Welcome to Study Time, a televised home learning program produced by Rwanda-based.
Hello, Senior 6 chemistry students. Welcome back. I'm Alan, still with you in the chemistry lessons. So we are heading in for a new unit, that is Unit 11, which is about solubility and the solubility product for sparingly soluble salts. Basically, this is an addition on the other units, Unit 9 and 10, which are about the solutions and determining their concentrations. So even this part, we shall be looking at the concentrations of the ions in solution. So we are directly going to lesson 1, which is about determining the solubility and the solubility product constant, KSP. So, as I had already said of our lesson, we shall be dealing with the determination or the titration. Please do not forget the knowledge about the indicator and the titration as we looked at in Unit 10. So, in today's lesson, we shall be looking at mainly two key terms, and that is solubility and solubility product constant, normally considered as KSP. So, as I had already told you, some of the things we shall focus on in this lesson are the definitions of those two, defining solubility, solubility constant, and other more definitions as you looked them in your ordinary level chemistry. Then we also look at the expressions for KSP. We determine it theoretically, see the methods used to determine it. Then we carry out calculations. I expect you to be ready with your calculators, of course scientific calculators, because we shall be using them now and again. So, what are our objectives today? There are actually three, but the prominent ones are the last two, as you see. The first objective is you should be able to define solubility and the solubility product constant. When you're done defining them, then we go ahead and formulate expressions for KSP, for salts of different combinations. We shall see when I talk of different combinations, I mean like sodium chloride has the valence of 1,1. So if you look at calcium hydroxide, we have calcium with positive 2. That would be different. For instance, if you look at it with aluminium hydroxide, with aluminium having positive 3. So when they combine with the OH, they give different ratios. So that is what I mean when I talk of different combinations. Then the third is to perform calculations accurately involving solubility and the solubility product constant, KSP. So those are the objectives that we are to work on in this lesson. I believe we shall achieve them with you being part of the lesson. So let's directly go to our lesson content, which is about solubility. But of course, this is not new to you. You looked at solutions and solubility in your ordinary chemistry or the ordinary level, so this is part of it. That's why I'm calling it revisited. We are checking it up, because you already have the knowledge. So when we talk of solubility, basically it's about get a solute, dissolve it in a solvent, then you get a solution. The solute molecules dissolve in the solvent molecules. Exact example in here, we all take, majority of us take sugar. I'm removing some people who are diabetic. Most of the time, they don't take sugar. But most of us take sugar. So you get 2 tablespoons of sugar, dissolve them in your cup of tea, it will dissolve. And then that, if the tea is made up of water, basically, then it will be making up the sugar solution. So in this case, sugar is the solute, then water, for instance, is the solvent, then you're making up the sugar solution. That is the elementary understanding. So when we come to the solubility in this case, we can define it as the maximum amount of the solute that dissolves in a certain amount of solvent at specific temperature. We have also to include those terms. If you're defining it, you don't need to miss those terms. Quantity of the solute, you must have a specified quantity of the solute, which you're adding it in already known amount of the solvent. So temperature needs to be maintained constant because any change in the temperature affects how the solute molecules will dissolve. You understand, for instance, the ladies who do cook, when you add common salt in water, it does not easily dissolve, but if that water is warm, then it easily dissolves. So that is the fact of temperature. Temperature activates the reaction. So when we're dealing with solubility, we have to maintain temperature constant. So that is the definition of solubility. So again, from your past knowledge, you know solutes can be either a gas, a solid, and sometimes liquids. Then solvents, they are mostly liquids. When we talk of mostly, we do not exclude other components where they dissolve only solids. For instance, alloys, you know the alloys, they are mostly solids. So in that case, we are only looking at solubility in terms of having your liquid as a solvent, then get your solute, dissolve in it. For the case of this unit, we're going to be dealing with solubility expressed in two categories. Either as the moles of the solute in a liter of solution. Remember at the start we talked of a specified amount of the solute and a specified amount of the solvent. So in here, when we're dealing with the solubility in this unit, we shall be talking of moles of the solute in a unit of, in a liter of solution, indicating we are quantifying the whole component. Or we look at how much of the grams of the solute that has dissolved also in a liter of solution. So those two are what you need to take in consideration as we go ahead with this topic content. We're still on the definitions. What is a solution? We've been talking of solution and solution. A solution, simply a solution is the one where the solute molecules have all completely dissolved. You do not have undissolved solute molecules. We are seeing the example in this illustration, this first test tube. You don't see any undissolved solute molecules in it, so this is a clear solution. But in this case, we call it unsaturated solution. And this takes me to highlight a few of those. So we have an unsaturated solution whereby you can still add more solute molecules and they will keep on dissolving. Then we reach a point when those molecules you've added cannot dissolve anymore. In that component or that solution is considered to be saturated. The molecules of the solute cannot dissolve anymore. And when you go beyond this point of saturation, that is where we have what is termed as supersaturated solution. You're going beyond the saturation point. So at that moment, some of the crystals start to form as a result of the salt or the salt molecules being excess in the solution. Our emphasis is about saturated solution because we are going to be using it now and again when we go deeper into the solubility. So what is a saturated solution? Two of the characteristics of it are you having the solute molecules in excess, so some remain undissolved. So you will always be having undissolved solute molecules in your saturated solution. So you have a solution, then some of the particles remained undissolved. So that is a point we shall be looking at. In simple, it sets up an equilibrium, as we're going to see it ahead. We're talking of sparingly soluble salt. This is, of course, a review. Remember, you had this knowledge from your previous lessons. So a quick review in here is, when we talk of a salt to be sparingly soluble, we can't eliminate other two terms that come along with it. One is soluble salt, sparingly soluble, then insoluble. You see, we're starting from what is soluble to what is insoluble. Then sparingly soluble is in between. So what is a soluble salt? Simple. It completely dissolves in water, forming a clear solution. This is the example. You don't have any undissolved molecules in it. It is clear. That is, when that salt dissolves in water and forms a clear solution, we call that salt to be soluble. Mostly if it is within an unsaturated state. A sparingly soluble salt, on the other hand, partially dissolves. What do we mean? It will set free some molecules or some ions, then it still has some other particles undissolved. A point to note in here, a sparingly soluble salt, at any one moment, it will always have undissolved salt molecules in its solution. I want you to distinguish it from the saturated solution. Yes, it will attain a saturation point when no more solid particles are dissolving. But before that point, for a sparingly soluble salt, it will always exist with some undissolved particles in its solution. That's a point to note. But of course, as you add more and more, they will reach a point where they will form a saturated solution. But what I needed to raise up was that factor. Then insoluble salt, for them, they do not dissolve. Instead, they form a suspension. This is a suspension. Some of the particles will remain hanging. I'm using that word hanging, but the scientific term is they are suspended in the solvent molecules, like as you see these dots. So we call that suspension. This clearly distinguishes a soluble salt solution, a sparingly salt solution, and an insoluble salt solution. So that is a quick review or a quick reminder on the terms we shall be using. If I can quickly take you back, remember a saturated solution, what it is, and remember a sparingly soluble salt. Those two go hand in hand. We shall be looking at them. So when you dissolve a sparingly soluble salt, will always exist in equilibrium, whereby you have undissolved particles of the salt with the solution. This solution will have the ions set free. That is something you need to recall of. So, solubility and solubility product constant. I had already told you about solubility, so now we look at solubility of a sparingly soluble salt. What is it? Clearly, the amount of that salt, either in moles or in grams, that dissolves in a liter. We need to quantify the volume of the solution. So when you get an amount that dissolves in a liter of solution, then it gives us the solubility of that salt. When we bring in the solubility product constant, is basically the mole concentration, the product of mole concentration of the aqueous ions from the sparingly soluble salt. What do we mean in here? As I had already said, dissolve your salt. It would set free some ions in the solution, then it remains with a salt. So it sets up an equilibrium. And that is where we have the solubility product constant. It is also affected by temperature like any other equilibrium aspect, and its units are formulated from the expression which we are just looking at. Expressions for the solubility and the solubility product constant. We have a general formula for the salt. That is the salt we're having. One may wonder what kind of salt is that. From your chemistry, you know if you have a salt of this category, the N is the charge on the anion, then the M is the charge on the cation. So when you dissolve it in water, it will ionize, setting free the metal cations in solution and the anions in solution. So it is balanced like this. Remember, it sets up an equilibrium because it is a salt in equilibrium. It is in contact with its solution. That's why we have this reversible reaction or reversible sign indicating even these ions can combine back to form the salt. And at the same time, the salt will continue ionizing provided something is disrupting the amount of ions. So if it reaches at a saturation point, then that equilibrium sets up and it becomes stable. So it forms what we call the solubility constant, Ks. Remember the principles of the chemical equilibrium? Being in equilibrium, it sets up that constant called solubility constant. And from those principles, we can get the solubility constant by looking at the concentration of the ions raised to their stoichiometric ratios. Look at M raised to N. N is the ratio when it ionizes. M is the mole ratio when it ionizes over the concentration of the reactant. But remember, this reactant is a salt, and by being a salt, that indicates it remains constant since at any one moment, this sparingly soluble salt will always exist as undissolved salt in equilibrium with its ions in solution. So the salt will always be there, and by that factor, it remains a constant. And this finally gives us the expression for KSP, which is simply the product of the concentration of the ions in a solution. And that's why it is actually called solubility product constant, the product, the multiplication of the concentration of this ion and this ion in solution of a sparingly soluble salt. Let's take a quick illustration with calcium hydroxide for you to understand the whole concept when we are talking of the expression. Look at calcium hydroxide. When it ionizes, because it is a sparingly soluble salt, it sets free the calcium ions and the OH ions. And at the end is, you see the mole ratio. When it ionizes, it releases 2 OH ions. So in the KSP for calcium hydroxide, we need to raise the concentration of OH ions to 2, to the power of 2, because of its mole ratio. And that is what the MN imply according to this general equation as you see the highlighter. So basically that is a quick example. So as we go to our other objective, which is determining the solubility product constant, I want to take you quickly about the other objectives. We've looked at the definitions of the solubility and the solubility product, which we said solubility, the amount of the solute dissolved in a liter of solution, then the solubility product constant as the mole concentration of the ions of the sparingly soluble salt in solution. Then we've just finished looking at the expression for solubility. Now let's see how we can determine the solubility product. Briefly, just get a saturated solution. We are using calcium hydroxide, for instance. Get a saturated solution whereby you dissolve some amount of the solute in water or in that solvent until no more dissolves. Then you will get a saturated solution. Pipette a known volume, in this case 25 milliliter. Add it in a conical flask. Add an indicator. Remember, this is basic, so you can use any indicator of your choice. Remember, we looked at the indicators. In this case, this is litmus, blue litmus solution. When you add it in, being a basic solution, it becomes light blue. Using HCl with a known concentration, you see the concentration, and that is what we call as standard solution. The HCl has its known concentration, starts titrating until the color changes. That is the end point. In this case, this is a blue litmus solution. It will turn to green at neutralization, as you see. So you will stop the titration. Then, using the volume of the acid and its concentration, you calculate the number of moles. Then you relate the number of moles of the acid with the OH from calcium hydroxide. So there you get the concentration of OH ions in the saturated solution of calcium hydroxide in this case. And you will get the solubility by using the equilibrium equation. As you can see, 1 mole of calcium hydroxide that ionizes, it gives 1 mole of calcium ions and 2 moles of OH ions, indicating if we know the concentration of OH, we can get the solubility, which is the amount of the ions set free from the sparingly soluble solution into the solution. So in this case, with that ratio, you can quantify the solubility, which would be the concentration of calcium ions, since it is 1:1, or a half of OH, since it is 1:2 in this case, and you determine the solubility. We can't go without trying a calculation for you to understand what we are talking of. Let's look at that example and do a few calculations. Of solubility. So we have that specific example. Let's quickly go through it. They're saying a saturated solution of silver chromate contains that amount, grams per liter, indicating this is the concentration in terms of the mass. So we have silver chromate. Okay, this is as a solid. When dissolved in water, it ionizes, giving silver ion. This is 1 with the 2 here, aqueous, and the chromate ion. So, balanced as that. That is part A, to write the equation, then the part B, to formulate the expression. Remember how to formulate the expression? Simple. It is the mole concentration of this, but multiplied, or what we call the product of the mole concentration. In this case, it will be the concentration of silver ions. Since it has the mole ratio of 2, it will be raised to its stoichiometric ratio and the chromate ion as simple. This is 1. So the units will be mole per liter squared times mole per liter, which directly gives us mole cubed per liter. This is a 3 power 3, like that. So that is the unit. The unit is derived from the concentrations. Next, we are to calculate the KSP. We are to calculate the KSP. So we need to get the mole concentration. We've been given the atomic masses. Silver chromate, its molecular mass will be 5108 plus, this is we multiply by 2 because it has a 2, plus chromium, which is 52, plus oxygen 16 times 4. With your calculator, very, very, very fast. 52 plus 64. You get 332 grams per mole. The purpose is to look for the mole concentration. And the mole concentration of silver chromate directly will be the mass that we are having, 0.024, which is gram per liter, over the mole concentration, over the molecular mass, which is 332 gram per mole. This will give us mole per liter, 0.024 divided by the answer, 7.228 times 10 power negative 5 mole per liter. So this is the concentration of this in solution. To get the amount of the ions, we shall use mole ratio. What do I mean by mole ratio here? For 1 mole of silver chromate that dissolves, it gives 2 moles of silver ions and 1 mole of chromate ions in solutions. It gives this and this, so indicating we can use this mole ratio to get the amount directly. So the concentration of silver ions will be equaling to it will be twice the concentration of silver chromate in a solution, and the concentration of the chromate ions will be equaling to the concentration of silver chromate. So with us having this and having this ratio, you simply substitute in the KSP. Please go on and substitute and get the answer. I want to follow it up in the next lesson and find the answer that you got for this. Go on and substitute. We are already having the concentrations of each. Substitute them in our KSP and get the answer. So that is it. Thank you for your participation. Again, I have to leave you with the exercise to practice, and that is it. Thank you. Stay safe.